A few more example problems involving straight line motion. We're told that the free fall equations for Mars, Earth, and Jupiter were given the position functions, and we want to know how long would it take a rock initially at rest to reach a velocity of 16.6 meters per second. So for Mars, we know that the position function is s of t equals 1.86 t squared, which means the velocity function for this would be 3.72 t, and the question is, when does this equal 16.6? And this is when t equals about 4.462. This would be seconds. And for our purposes, we will always round to 3 decimal places. There are no exceptions to that. Well, there are exceptions, but unless otherwise noted, always go to 3 decimal places. For Earth, same situation. If s of t is 4.9 t squared, then the v of t is 9.8 t. And we want to know when that equals 16.6. Dividing, we find that this occurs when t is about 1.694 seconds. Again, always go to 3 decimal places unless otherwise indicated. Finally, for Jupiter, s of t is 11.44 t squared, and we're trying to figure out when will the velocity be 16.6. So we've got 22.88 t, and that will equal 16.6 when t equals 0.726 seconds. Now a different example. This one involves a rock that is thrown vertically upward. So in this example, a rock is thrown from the surface of the moon vertically up. Initial velocity is 24 meters per second, and its position is given by this, right, the height. And first we want to find the rock's velocity and acceleration as a function of time. So velocity is the derivative of position, so it would be 24 minus 1.6 t. And the acceleration is the derivative of velocity, so the acceleration would be negative 1.6. In B, we want to know how long did it take the rock to reach its highest point. So for part B, first we need to know when does the velocity equal 0, and solving for t, this occurs when t equals 15 seconds. So that's how long it takes for the rock to reach its highest point, because that's when the velocity is 0. How high did the rock go? Well, for part C then, how high did it go? Well, s of 15, plugging 15 into the position function, would give us 180 meters. D, how long did it take the rock to reach half of its maximum height? Well, so how long did it take for the s of t to equal 90? When did 24t minus 0.8 t squared equal 90? Well, if it took it 15 seconds to get all the way up, you might think that it's going to be at 7.5 seconds, but remember it's slowing down along the way. So we have this quadratic that we need to solve, and so this one will be kind of messy, but when we set it equal to 0, we've got this 0.8 t squared minus 24t plus 90 equals 0. We can use the quadratic formula. We could try to factor this. We could use completing the square. But when we solve this for t, we'll find that this occurs when t is about 24.393 seconds is when it gets halfway. How long was the rock in the air? Well, if it took it 15 seconds to get up, it'll take it 15 seconds to get down. So it's going to be, for part E, a total of 30 seconds. Well, that doesn't even make sense. Let's strike that. Let me erase that. That can't be true. That initial velocity changes some things. So we want to know, when does it hit the ground? So again, for E slash that initial thought, we want to know when is 24t minus 0.8t squared equal to 0. When we factor out a t, we'll have, what a mess, t times 24 minus 0.8t equals 0. For this part, it's t equals 0, and for this other part, it is that t equals 30 seconds. Finally, find the rock's speed when hitting the moon. So for the last part of this question, we want to know what is v of 30, and that is whatever 24 minus 1.6 times 30 is, and you'll find that it is negative 24 meters per second, because it reaches the same speed as it was when it was going up. Third example requires us to have a clean slide. And we've got a ball, and it's dropped from the top of Mount Washington, so it's just accelerating down, which is 555 feet high. How long will it take for the ball to hit the ground? So we know from a previous problem that the acceleration due to gravity is negative 32 feet per second squared, and we're using the feet because that's what our height is in, which means that the position function is going to be negative 16 t squared plus v naught times t. Well, v naught, since it's dropped, is 0. So it'll be 0 times t plus the initial position, which is 555 feet high. So there's our position function. We want to know how long it will take for the ball to hit the ground. We want to know, when does this thing equal 0? Negative 16t squared plus 555. And if we solve this for t, what we will find is it will take about 5.890 seconds for the ball to hit the ground. What is the ball's speed at impact? Well, its velocity at impact is the derivative of the position function, so that will be negative 32t. And v of 5.890 then must be about negative 188.48 feet per second. It's about that because we use a round number. Our final example for straight line motion involves a roller coaster. And there's this special roller coaster which only moves in a straight line, and the position of the car is s of t equals negative 0.01 t cubed plus 1.2 t squared, and it only functions for the times between 0 and 120, which means that the ride only lasts 2 minutes. So part A, we want to find the velocity and the acceleration of the coaster. Velocity is the derivative of position, so this would be negative 0.03 t squared plus 2.4 t for the velocity, and the acceleration, the derivative of velocity would be negative 0.06 t plus 2.4. When is the roller coaster stopped for part B? Well, the roller coaster is stopped when the velocity equals 0. So when is negative 0.03 t squared plus 2.4 t equal to 0? If we factor out a negative 0.03 t, we'll be left with t minus 80, which means it stopped at t equals 0 and t equals 80 seconds. When is Paul speeding up and slowing down? Well, we need to consider some things about acceleration here, so let's find when acceleration equals 0. So when does negative 0.06 t plus 2.4 equals 0? Well, this will happen when these two are equal, which is at 40 seconds. Okay, so we've got our velocity graph to consider. We'll go from the important points are 0 and 80, and our acceleration graph, important points are 0 and 40. And if we test a number like 1 for velocity, then we're going to find that the velocity is positive between 0 and 80. And if we test a number like 81 for everything after 80, we're going to find that the velocity is negative after 80. If we do the same for acceleration, what we're going to find is that the acceleration is positive between 0 and 40, testing the number 1, and it is negative after 40, testing the number 50. So Paul is speeding up when everything is working together. So that would be from 0 to 40, he is speeding up because both are positive, and from 80 to 120 because both are negative. I'm not really sure what's happening at 120. Maybe it's just kind of moving. The machine's off. Who knows? And he's slowing down when everything's working opposite. So this would be from 40 to 80. He is slowing down. And finally, where is Paul at critical times of his ride? So critical times and critical points are always the end points. So in this case, we would want to look at s of 0 and s of 120. Those are the end points of the entire thing. When the derivative equals 0, so this would be at s of 80, what's going on there. And perhaps when the acceleration is 0, s of 40. And so to answer the final question, where is he at each of these times, we're just going to plug these numbers in to the position function, and we'll find that he's at 0 at 0. At 120, he's back at 0. And then at 80 and 40, he would be at 2,560 and 1,280. I'm not exactly sure what this means, but maybe distance from the starting point at both of those times. So there's all of our examples for straight line motion.